Hello guys, welcome to physics. This is high school physics. Here we are. And what are we doing today? Electricity. Okay, lots to get through. We've got to try and understand the following things: charge, coulombs, GLE, that's gold leaf electroscope. Looking at something called induction, that's how we charge the electroscope. Then we've got conductors and insulators, current, voltage, and resistance. Hello, resistance. We're going to introduce resistance if we get time, but we might leave that to our next video. So let's pitch in and see what we can do. Let's flick around with these screens as usual. And charge. Okay, electric charge. There's two types of charges, positive and negative. No surprises there. Okay, we measure charge in coulombs. And really what happens is this, you lovely, lovely people, is, remember that stuff we do in chemistry stuff? Well, you know, in your atom, you've got your nucleus and you've got your protons and your neutrons all tucked away in there. And you've got your electrons zipping around the outside. Okay, so the electrons are in orbit. They go around about 1 billion times a second. Okay, difficult to say exactly where they are at any particular time. But anyhow, the positive charges are tied in very, very strongly into the nucleus. The electrons whiz around the outside. So it's the electrons which are negative. Okay, it's the electrons which we move with the charge. Okay, we don't move the positive, we move the negative. So if you've got an object which has got positive and negative charges over it, if we come along and take away the negatives, then the object becomes positive. Okay, we don't put positives onto it. Okay, conversely, if we have an object and then we manage to get more negatives on it, then they cancel out these positives and the whole object's left as negative. Okay, it's only the negatives which move because they're in orbits and it's easy to zip them out of the orbit. Okay, we measure it in coulombs. That's the measurement of charge. Only the electrons move. Yeah, and now we're going to look at the gold leaf electroscope. Now guys, I don't have one handy, which is a bit of a shame, but just have a look at one on Google. Googly what's it? Mrs. Google will have a picture for you. Okay, go and chat with her, and you can see one. But they're a box about this big. Yeah, it's like that. Okay, and it's got metal sides and a glass window at the front, and probably a glass window at the back. And it's got a little stem inside it, about the size of a pen. Okay, and the stem goes inside. It's got a metal cap on the top, so it looks like a T shape. And it has a little bit of gold down here just attached onto the stem. All right, so it's called a gold leaf electroscope. We use gold because it's really malleable and we can beat it into a very, very thin sheet. All right, so and when we draw a gold leaf electroscope, so that's what a GLE is, gold leaf electroscope, we draw the T shape like that. Okay. But in reality, it's got a rubber bung here to insulate this from the glass case. The glass case goes around like this. Okay, this is a little bit longer. And then down here, there's a little bit of gold leaf. Okay, that's why it's called a gold leaf electroscope. And what happens is we come zipping along and we put a great big charge on here, negative charge. The negative charge spreads down here. Okay, like charges repel. And this leaf moves out, okay, because of those negative charges. If it was positive, be the same thing, all the positive charges, and we would get positive charges by removing the negative ones, okay? Either way, the leaf deflects up to here. If we neutralize this by adding negatives to all of these to cancel them out, the gold leaf just goes flat again. All right, so the angle of the gold leaf tells us how much charge is there. It's just an approximation, all right? It's qualitative, not quantitative, all right? It just shows us something's going on, but it doesn't give us a really good measurement, okay? So if we want to move things, we need a conductor. Conductors have lots of electrons. They allow us to move things. Insulators have lots of electrons, but they're difficult to move. so they're bonded in tightly and they're not easy to move. So plastics, rubber, wood, things like that, insulators, conductors, metals, and carbon. All right, that's it. Induction. Right, I don't know, scribbling over here, guys. So we're just going to try and squeeze in induction down here. All right, so with the gold leaf electroscope, we're only interested in this T shape. And the way it works is like this, right? We get our gold leaf electroscope, ignore the rest of it, okay? And then what we do is we bring up a charge. So to bring an object up on an insulator, because if it's on a conductor, the charge would rush down my hand into the ground. So for argument's sake, let's bring in a positive charge. So it could be a piece of polythene covered in positives. Okay, now opposites attract. So this is covered in positive and negative charge. The negatives rush up to the top. They'll go, yippee, this is the place to be, guys. Okay, they go rushing up there. And the positives, the negatives go to the top towards the positives. This leads positives down here. And the positives all group around here because they get repelled by these ones. Opposites attract, like charges repel. The positives all go down here. The gold leaf moves up in the air. No problems. Right. The next thing we do is this. We touch. We keep everything like that. And then we come along and we touch that plate. Okay. So what happens is this. There's our gold leaf electroscope. And now we earth the plate. Okay. Now, if you're in America, we call it a ground. So the earth symbol is like that. And in some places, it's drawn like that. Like in North America, they draw it like this. But that's our earth. We just touch the plate. It doesn't kill us or anything, guys. All right. Just it means the charge can move. So what happens? Well, we tell little lies, as often as we do in physics. We say these positives want to escape these positives, so they go down into the earth. Now we say that, but technically what happens is heaps of negatives come up and they cancel these out. Okay, so whichever way we tell the story, whether we pretend the positives move and go down here, or whether we tell the truth and say the negatives rush up and cancel these out, what happens is the gold leaf drops down flat. Okay, and that's because the negatives are held in place by the positives which are on that object. Okay. Okay, there it is. Now we remove the earth. We remove the earth and we remove that object, and the negatives then spread out. So what do we end up with? We end up with our gold leaf electroscope like this, covered in negatives. Ding, 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 like that. Okay, that's it, guys. That's charging by induction. We bring up an insulator which is charged. We earth it. We hold this in place. Remove the earth. Remove this. You remove the earth first, guys, because we need to hold these in place. Remove the earth. That will hold these in place, and then remove that. And the negative spread out. There it is. We can use a positive charge to charge something up negatively. We use a positive charge to charge it up. If we wanted to charge it up positively, we would just rub this against the T-bar, okay? This part of the gold leaf electroscope. If we wanted to charge this up positively, if we rubbed it against there, the negatives would all jump onto here, okay? And then they'd leave positives on the gold leaf electroscope. So if you want to do that, you have to actually touch it on there, but you can do that. So you can use a positive charge to charge it up positively, or a negative to charge it negatively, or we can charge by induction. Okay, but this doesn't touch. That's it. Right, moving on. Electric fields. Guys, if you have a point source here, here's our point source, and we charge it up with a positive. There's a little positive in the middle there. The field lines go out. If it was negative, they'd go in. If you had a sheet of metal and another sheet of metal connected like this, the field would be nice and uniform. It would go across the parallel plates with a little bulge at the end. Doink, like that, and dink, like that. Okay, so that would be it. That's electric fields. Moving on. current. Now, guys, you've heard of static. If we were to charge up something with static electricity, the electrons wouldn't move. Static, it means it's stationary. Okay, so what we end up doing is this. We want to get this charge moving. If we make the charge move, it's the electrons. Electrons are negative, so electrons go from negative to positive. Okay, so in a circuit, we have a little old circuit there. There's our battery, and there's a lamp. All right, and we know the current goes that way, goes from positive to negative. Okay, but the electrons, they go the other way. Electrons are negative, so they're made here, and the electrons go that way. All right, now, why is that? It's because back in the day, when André Marie Ampère, okay, our French scientist, okay, was investigating electricity, because which way does it go? I don't know. So he said, let's make it go this way. It was 50. He got it wrong. Yeah. All right. They didn't even know what to call it. And so they called it, what we call it? We call it after him. His name's Ampere, which we call it amps. All right. They called it intensity. They didn't know what it was, guys. A brand new thing they were investigating. They called it intensity. So when we talk about current, we give it the letter I for intensity. What is it? It's electrical intensity. Yeah, good call, guys. But we measure it in amps after good old Ampere, whose birthday was almost his birthday coming up, guys. January the 20th, 1775. All right, so yeah, if you're watching this on January the 20th, happy birthday, Ampere. All right, so there it is. That's what happens. We get conventional current goes positive to negative. All the rules are made up with that, but the electrons, they go negative to positive. Not tricky. All right, so the current goes positive to negative, but the electrons go the other way. The current intensity, we don't use that word anymore, but that's what it was traditionally, is the amount of charge divided by the time. Okay, the current equals the charge, the amount of charge moving divided by the time in which it moves. Okay, and if we want to measure it, we're using an ammeter, and we put our ammeter in series there, and it will just read amps. Easy peasy. Good. Let's not hang around. Voltage. Now, guys, difficult to describe voltage. We sometimes call it PD, meaning potential difference. Other times we call it EMF, electromotive force. Okay, that's the total amount of voltage that is being produced by a device like a battery or a cell. Okay, you can think of it as a push, right? It's not a push, but that's a way we just to describe it. It's just what gets the current moving around the circuit. We need those electrons to move. They don't want to move. Why would you want to move? You're an electron, you're quite happy just sat there. So the voltage comes along and it gives those electrons a nudge. Yeah. All right. So it's a push or even like a pressure. Some people call it a volt pressure. Yeah. And that's all the voltage does on a completed circuit. It pushes the electrons around or creates a pressure so they move. 1 volt means you've got 1 joule of energy being delivered for every coulomb of charge, right? Now, if you don't get your head around that, don't worry. Yeah, it's not going to stop you from, living a full and happy life. But if you can remember that, that crops up in exams. They say, what's the definition of a volt? And you go, it's a joule per coulomb. Write it down, get the mark. It doesn't matter if you don't really understand it, but you get the mark, which is really important. Yeah, come on, guys. You don't know how the internal combustion works, but you're quite happy to jump on a bus and go somewhere. You don't say, oh, I'm not getting on this bus until I understand how the internal combustion works. Okay, so just use it, get your mark. Voltmeters, they are wired in parallel. So if we put a voltmeter in, it would go in parallel there. Okay, right, what's under this one in the corner? Okay, introduce resistance. Resistance, guys, is just what it says. It impedes the flow of the current. So that we work out the resistance, it's V divided by I. All right, and we're going to come on to that another time. Okay, so we're just saying quick hello to resistance. That's another story, but it just hinders the movement of the current. And we measure it like this. Okay, have we covered everything? Let's have a quick look. All right, it said we were going to understand charge. Yes, we did. It measures in coulombs, the gold leaf electroscope. We can use one charge to charge something with an opposite charge. Yeah, remember, work through that sequence. Okay. Conductors, insulators, electrons don't move, they do move. The current is the amount of charge moving per unit time. Voltage is the push. Hello, resistance. We're going to come and talk to you another time. Okay, that is it, guys. If you've got any questions, ping it into the old question box. Someone will answer them for you. And until next time, have a great day. Goodbye.